Hello and welcome to the Machine Learning Podcast, the podcast about going from idea to delivery with machine learning.
Your host is Tobias Macey, and today I'm interviewing Kevin Stumpf about the challenges and promises of real-time ML applications and the work that he's doing at Tecton to help support them. So, Kevin, can you start by introducing yourself?
Yeah, for sure. Happy to, and thanks for having me. I am the co-founder and CTO here at Tecton, and with Tecton, we help organizations get real-time machine learning applications into production with our feature platform. Before starting Tecton, I was over at Uber, where I helped build the central machine learning platform team called Michelangelo.
And do you remember how you first got involved working in ML?
Yeah, the first time where I got really deep into it after taking grad school classes and whatnot on the topic was roughly 10 years ago now when I co-founded a trucking startup. We were actually matching long-haul truck drivers with shipments that shippers or brokers needed a truck driver for. And we used machine learning to predict prices because oftentimes we didn't have accurate pricing information. And so one of the most curious things that truckers are interested in is, well, how much am I going to get paid for its load? And so we try to help them out by having an ML algorithm that predicts the prices. And then through that startup, I eventually ended up at Uber, where I, as I just mentioned, was part of the central machine learning platform team, Michelangelo, which helps pretty much all the different ML teams at Uber get machine learning into production. And that does everything from predicting ETAs when you open up the Uber app to recommending which restaurants you may want to purchase from an Uber Eats, pricing predictions, etc. There's a whole long class of different ML problems that are solved with Michelangelo.
And in terms of the focus for the conversation today on real-time ML, I'm curious if you can describe a bit about what that is and how you might differentiate it from other approaches to machine learning that folks are using.
Yeah, real-time machine learning should really be contrasted to batch machine learning, or also sometimes called offline machine learning. Real-time machine learning, I'd classify as any application that uses machine learning where the machine learning prediction affects the end user immediately, right in the moment where that prediction is being made, and not hours later, days later, or whatever it is. And common examples here are real-time transaction fraud detection, where somebody's swiping a credit card somewhere and it's either immediately denied or accepted, or it's real-time recommendations where the items that you've just clicked on Amazon affect the next recommendations that you get on the page that you're going to browse a couple seconds later, or dynamic pricing systems which react to the movements of supply and demand literally in the moment. If you look at the ride sharing applications out there, real-time bot detection, all that type of stuff. So all of these are applications where the prediction is made and the end user is immediately affected by it. And when you look at the offline machine learning, that's typically where a common example would be maybe you run a model in big spikes in batches, like once a day, once a week or something, where you look at all of your customers and you predict their likelihood of churning, and then you may send them an email with a coupon code or something like that.
And in terms of the kind of utility of real-time ML, I'm curious if there are any common categories of problem that it lends itself well to, or particular industries that have a higher predominance of using real-time ML, and just some of the ways that people should be thinking about whether or not it is a suitable fit for the problem that they're trying to solve.
The best thing to think about is actually where, and you can use your human intuition honestly for this, which is where do you have most of the information that will help you make a prediction about something that you want to predict, like say a recommendation, or whether you want to detect fraud in a transaction. Is that information very new, very fresh? Is that information that's basically just come into existence a couple seconds ago, a couple minutes ago, a couple hours ago? Is that the type of information that you, if you personally had to decide and personally with infinite time had to make a recommendation without a computer, is that the type of information you would use in order to make that human prediction, so to say? If that type of information has only come into existence in the last couple of minutes, hours, up to milliseconds ago or up until right now, then that's typically a good use case and a good case for real-time machine learning. If on the other hand, you'd say, hey, the like 99% of the wealth of information is just buried in what the user, what I know about the user since the Big Bang up until a week ago, then, and I only need to react to that information in batches once a day, once a week or something like that, then that's a good case that, hey, that's probably that is best served by batch machine learning.
And as far as the technical and organizational requirements for being able to actually take on this real-time ML workflow, I'm curious, what are some of the additional complexities or maybe even in some case simplicities that get incorporated into the supporting infrastructure and architecture to be able to actually start thinking about these real-time predictions?
Yeah, when we look at the operational and organizational requirements before we look at the scope and the architecture of these real-time ML applications, at the end of the day, real-time machine learning really covers four different parts. One is it touches the operational system. That's the system in which your microservices are running, or the other production applications like your backend system, your Postgres database, all the stuff that cannot go down, that's mission critical, is in the operational stack. That's one. Then there's the data pipelines, right? Like somebody needs to actually calculate machine learning features, run training pipelines, make predictions. And that typically sits next to your organization or close to your organization's data engineering efforts and other data pipelines, whether they're batch or stream. Then it also touches the observability parts of your organization, because you need to know whether your model is going off the rails or not. And then finally, of course, data science is involved, because somebody needs to come up with the ideas to how to train a model, what features to implement, etc., and then finally train the model. And so you've got these four things: operational system, data pipelines, observability, data science. And your organization needs to be set up to cater to all of those for real-time machine learning. And so typically what you'd find is that you either have like trios of people, like a data scientist and a data engineer and a software engineer work together, or some lucky organization have them all baked into one in like the form of a machine learning engineer. Some platforms, like obviously Tecton, is trying to make that significantly easier, so you don't need as many folks with different backgrounds and whatnot to actually power real-time machine learning. But good indicators that your organization is actually ready for real-time ML is that you can already spin out APIs and services with ease, and you follow DevOps best practices already, and all that stuff is not very foreign to you.
And real time as a term in the technology industry is always interesting because it's always so fraught and overloaded with concepts and kind of different applications of use. And so far, what we've been talking about with real time ML is focused on being able to take data as input that was generated recently and then generate a prediction from it. There are also elements of ML or applications of ML that might be considered real time, as far as things like reinforcement learning, where you're actually actively updating the model itself with data as it is generated, or kind of streaming ML, where again, you're constantly kind of retraining the model and you never actually go back and do a big bang, retrain the model, deploy it. And then so you're constantly evolving the model as it sees new data. And I'm wondering if you can talk through maybe some of the nuance of these kind of three different categories of how you might think about real time in this context of an ML application.
Yeah, and at the end of the day, it really just comes down to terminology and what you include and what you exclude. And personally, I include in real-time machine learning anything where you have a model that's making a prediction online, even if it's just acting on pre-computed batch features. It doesn't have to act on like real-time data or streaming data. It's totally fine if it just acts on pre-computed batch features, for instance, to make a prediction in the operational online system. and that has been most helpful in having conversations with our customers to differentiate it from batch machine learning. Reinforcement learning, or like somewhat related, is like online learning where you're continuously updating the model as it's running in production. I would generally classify that also as an online system. It's certainly acting online. It's in the operational world where it's continuously acting on new information and updating itself. To be frank, it's something that I basically never see in production use by anyone. It's super heavily touched upon in the research field, but I think this is an area where research is many, many years ahead of actually industry. And there are some companies who, of course, use it. Google, I know Twitter has some online learning systems and whatnot, but by and large, the vast majority of real-time machine learning applications don't leverage these mechanisms yet.
And as far as the actual model architecture of what you're deploying to be able to do these kind of low latency predictions, I'm curious how those constraints and requirements influence the, I guess, styles of machine learning algorithms that people are able to employ. So thinking in terms of like stochastic models versus deep learning, et cetera, as well as the size of the model that is kind of viable to be used in this context. So again, thinking in terms of a random forest versus ChatGPT or something.
Yeah, actually, the whether you look at the decision trees like your XGBoost or the linear models or the deep learning models, at the end of the day, that can all be used, and they all are heavily used in real-time systems. Yes, there is certainly a very big difference in the inference cost and whether you need a GPU cluster under the hood or whether a small CPU is enough to quickly enough make the inference, but they can all be used for real-time applications. The size of them is, of course, different, and your ChatGPT model is going to be significantly larger than your good old linear regression. But they can all be used, but the operational complexity is, of course, a little bit or significantly higher the more complex the model is.
And the other interesting element of using machine learning in this online mode versus a batch workflow is the potential for things to go wrong, where, obviously there are some notable examples of like the Tay chatbot, where it's continually learning and trying out new things, but also just in the case of, maybe I have a bad batch of data that made it into my feature store, and so now I'm giving erroneous predictions or recommendations. And just curious how the kind of failure modes and guardrails around machine learning models need to be thought about in this online versus batch context.
Yeah, one of the biggest failure modes here is train serve skew. And train serve skew, for those who are not familiar with it, basically means that you're training your model on data that looks different in its shape or form from the data that you make predictions with in the production system. If there's a skew, then your model basically is not set up for success because it sees completely different shapes and forms of data in the production system, so it doesn't know what to do with it. So the prediction is going to be a flip of a coin, basically. And it's very hard to notice that because you're not going to get a exception, say, from the model running the production system. It's not going to know that it's never seen anything like it. It's just going to do its best and make a prediction, and it's very hard to identify these types of issues. And so train serve skew is very easy to introduce with real-time machine learning, and significantly easier than with your common batch or offline machine learning application. And one funny example that I have here is we talked to one company where one of the large consulting firms came in, and it was a big bank, and they went in and they trained a model for them. I think it was a fraud detection model. The model was trained, put in production, and then it just ran in production for literally years, and it was never retrained and updated. And nobody actually looked at whether this model is going off the cliff or whether you're leaving a ton of money on the table by not retraining it, which is almost guaranteed to be the case. And the reason why I'm bringing this anecdote up is that with real-time machine learning, it's extremely easy to just not continuously retrain your model. Just train it once, you throw it behind an endpoint, and then you let it run in production rather than retraining it frequently. Versus with batch ML applications, what I most commonly see is that a lot of companies actually they retrain the entire model before they make batch predictions. And it's just all the same Jupyter notebook or the same Python file that's running on an Airflow. Just retrain the whole thing and make a prediction. And as long as it's not cost prohibitive to do the retraining step, it's actually not a bad idea to do that and to include the information that you have up until the point in time in which you're making the predictions. Besides retraining, another thing that's important to keep in mind is that with real-time ML applications, one of the biggest challenges is that you need to calculate the features both for your training pipeline, which runs offline, and for your inference pipeline, which runs online. And so you need to be able to provide the feature values to your real-time machine learning model that's running in the production system at super low latency, right? Like you need to be able to provide this feature in a handful of milliseconds with high availability, while offline, you just crunch through a ton of data in huge spikes as you generate the training data. So to make this a bit more concrete, what you would typically do if you have a real-time feature or a streaming feature is in the production system, you may run a Flink streaming job or a Spark structure streaming job, or maybe just run some Rust code that's executing your transformation in real time. While offline, you re-implement everything using, say, Snowflake SQL because all of your data is in your data warehouse. And now you have to make sure that the two implementations are identical, because if they're not, you introduce train serve skew. That's very hard to debug, and your model performance may be awful or not as good as it possibly could be. So those are two very common failure modes that are very easy to introduce with real-time machine learning. And best avoided, of course, with something like a feature platform.
And as far as that kind of train serve skew challenge, it also feeds back into the question of data quality, particularly in an ML context where the quality of the data is a huge predictor of the quality of the output model. And I'm curious how teams are addressing some of the question of how to kind of identify the critical elements of what quality data looks like for a given model, and some of the kind of monitoring and ongoing validation that needs to be performed as new data is fed into the platform, so that you can, for instance, maybe, shunt bad data into a dead letter queue to be reconsidered, or, factored into updated experimentation, and just some of the aspects of kind of ongoing validation and maintenance of the model as it continues to serve, without having to kind of take it down for maintenance or have it be spitting bad predictions for X period of time without being aware of it.
When it comes to observability and monitoring with machine learning, I'd broadly look at three different categories. One is just data quality monitoring. The next one is prediction monitoring. And the next one is operational health monitoring. Operational health monitoring is what we already know from how we run microservices in production. Like what do the serving latencies look like? What does the uptime look like? In the case of a feature store, a feature platform, what does the feature freshness look like that I'm continuously serving? All of that I would bucket under operational health, where if things go off, oftentimes you have a provisioning issue, or you're running on an unhealthy node or something like that. So that's super important to monitor, because if that's going off the rails, then your predictions you're not gonna get good predictions. Then there is model prediction monitoring, where you want to make sure that the prediction that you're making is still having a positive impact on the business situation where you want to create value. Like, are my recommendation predictions, are they still serving the business? Like, am I still selling as many items as I expect to? Like, what's my click-through rate on the recommended items? And if those are suddenly, if the click-through rate is suddenly falling off the cliff, then you have a problem, which may very well be related to your model. And then the third is data quality monitoring associated to it, which is like, what does the quality of the features look like that is being fed into the ML model? And here you can again bucketize, and you can either say, well, do I have full-on outages where maybe there's no data coming in, or the distribution of my ML features is now, or the statistics now look completely off. Maybe I'm suddenly multiplying the user's age by 100, and that's not anymore within the range and the schema that the model expects. So those will be full-on outages. And then a separate category under these data quality issues is drift, common problem in machine learning, where the data may still be real and representative of reality, but it's shifted over time, where maybe your user's preferences have just shifted over time, and you really ought to now retrain your ML model, because your model just hasn't seen these types of distributions, these types of means and standard deviations or categories of your ML features before, so it needs to be retrained. And so a sophisticated solution should monitor all of these elements. Of course, that's quite a lot, and that's why platforms and tooling helps you. But those are the different areas where you want to have visibility in order to make sure that your model isn't going off the rails.
And for teams who are trying to build these types of systems, I'm curious, what are some of the gaps in knowledge or understanding that you see them commonly encounter, and maybe some of the useful patterns that they have built up to be able to account for some of these error cases and failure modes, so that there is kind of a general team understanding of how to address these systems and build them robustly, versus the kind of the cowboy case of, hey, I built this model and put it in production, isn't it swell? And then everything just breaks.
Yeah, I think the worst things here are the silent errors. The loud errors are, even if you don't think about them, you'll realize them when they're in production. And the loud errors I'd classify as suddenly your latencies are going through the roof, and so you're not able to make the item recommendation within the 200 milliseconds that the rest of your team needs it. Or maybe the prediction isn't returning anything useful and you're recommending garbage. Those will be the loud failure modes, which are easy to detect. The silent ones, where you're silently introducing train serving skew because you're not monitoring properly the quality of your data. Those are really, really tricky to detect. And so you better have a good data quality monitoring solution in place. And again, here it's not enough to just have data quality monitoring solution, because that may just show you that your batch data that you use for training is of good quality and doesn't change. But you also need to make sure that you are, at prediction time, calculating your features the exact same way. And that's why, of course, I would recommend to anybody to use a feature store, a feature platform, to minimize the risk of introducing train serve skew simply by incorrectly calculating the feature values or having differentiated implementations between serving and training. And so takeaway here should be like data quality monitoring, super important. And then second, have a feature platform or a system where it's guaranteed that the implementation of your serving features and your training features is identical. Because if you don't have these systems, silent errors will eventually smuggle themselves into your system that are really, really, really hard to detect and very hard to debug.
And in terms of the kind of featureization strategy, what are some of the useful tactics in terms of being able to actually build the features in such a way that they are debuggable and composable, so that you don't have some giant complex feature that you can do kind of a surface level validation of, hey, this gave me a feature and it's within a range that I think I expect. But then as time goes on and you undergo the issue of kind of inevitable data drift because the world moves on, you kind of waste a lot of time with debugging things until you get to the point of, hey, it's this feature and I'm putting too many different conflated requirements into it.
Yeah, two things I'd say here. One is it's important to not only monitor the quality of your predictions and the output of your model to see, hey, are they suddenly looking super different? Are the distributions of my predictions suddenly shifting entirely? But it's extremely important to look at the inputs to the model, because typically for every single one prediction, you have on the order of tens, hundreds, thousands, maybe even higher than that order of magnitude features. And you want to know which one of those is changing, which may at the end of the day affect the quality of your prediction. And so may even have some leading indicators here in your feature where you don't quite notice it yet when you just look at the model's performance. And so that's where modularity in a way, or really more granular monitoring, comes in. You just want to break it up and look at the feature quality and not just the prediction quality. And then apart from that, you touched on modularity and feature engineering. And here, of course, it's important to try to use a system where you reuse individual building blocks of your in your feature engineering system, where everybody doesn't re-implement customer lifetime value or 30-minute transaction count feature on their own, but they all have the same common understanding of what the definition should look like and share it and reuse it. And then similarly, if you have derivatives of features, they should depend on the literal feature implementation rather than have a redundant and copy implementation of the upstream computation. And so you should manage those features in code, and feature engineering transformation should be managed in code backed by Git, etc. And use common software engineering principles to keep it dry, to not repeat yourself, and to reuse whatever you can.
And I guess in terms of the experiences that you've had of working with customers who are starting to go down this path of building machine learning systems, wanting to be able to react, promptly to input data, what are some of the kind of pitfalls that they have encountered and some of the useful mistakes that you have seen people make that you and others have been able to learn from?
Yeah, the most common mistake is just always forgetting the train serves queue issue, or to start with a system where you say, oh, it's going to be good enough. I don't need to think too much about my foundation. I'm just going to hack something up, put it in production. And then you've got the stickiness effect of your application that's running in production and it's not implemented using good practices. And then it's going to be pretty hard to replace later on with good practices where you can avoid train serves queue. Another thing that's quite interesting is when you look at real-time machine learning, the real-time data processing industry as a whole is actually still far behind the batch processing industry, right? Like when you look at the Sparks of the world, the Snowflakes of the world, we're really good now at conveniently processing large amounts of data. Like over the last 10 years, 20 years, we've come a long way from the map reducers of the world to just being able to write a simple SQL query that can easily process terabytes, petabytes of data. And we kind of forget what that all looked like 10, 15 years ago when you had to implement individual Java applications to do any MapReduce type stuff. Streaming today is still pretty hard. And it is a significantly harder challenge because you're dealing with fundamentally unbounded data sets. Like a batch data set is bound, it's limited. You know exactly how many rows there are in there. Of course, it can be growing, but you can arbitrarily slice it, while streams are unbounded. And so when you think about things like stream aggregation, stream joins, etc., those are hard problems. And there are a lot of different players who are out there and who are trying to make stream processing easier, but those aren't really deeply proliferated yet. And that makes it harder to introduce specifically streaming features in machine learning applications. Of course, Tecton, we have our own answers to make that simpler for customers to express common streaming machine learning features. But as a whole, that has just been a pretty interesting realization after having come out of Uber, where we had a pretty sophisticated streaming stack, on how immature the industry generally still is.
And in your experience of building Tecton and helping customers through this journey of being able to build and deploy these real-time ML systems, what are some of the most interesting or innovative or unexpected ways that you've seen that capability applied?
One of my favorite use cases is from our friends over at Vital Systems, where they use Tecton or real-time machine learning to assign patients to hospital beds, which is just like a really good cause that can actually save lives, which I really like. And apart from that, I'm also always excited to see, and sometimes surprised to see, when I see safety applications of machine learning. So it's not just about fraud detection, but it's literal end user safety, whether that's the safety of a rider of a Uber trip, or the safety of someone who's playing a game where you can literally predict whether somebody could be potentially under in a potentially harmful situation that you may want to do something about. And those use cases aren't all too commonly talked about, but I love seeing those. And then maybe finally, one thing that I also find always interesting is when I look at customers who use feature stores, is oftentimes what comes before you have a machine learning model is running in production is that you actually have a human implemented heuristic, a rule that's making a decision based on input data, which can actually get you quite far as well. And these rule-based systems, they also need to act on data. That's streaming data or batch data or real-time data. And we see customers actually use Tecton as well to power some of their rule-based systems before they're ready to upgrade those to machine learning driven systems.
In your experience of working in this space, I'm curious, what are some of the notable evolutions in terms of kind of capability and functionality and some of the future potential that you envision once we do get to a point where these kind of streaming data systems are more on par with batch capabilities?
Yeah, the future that I have in mind is one where you can look at an organization's data systems, and you basically see this giant web of with nodes and edges that connect to different nodes, and every node is a data consumer or a data producer, and the edges are the actual data processing. And it doesn't matter whether it's streaming or batch, but you've got the full lineage graph. You see exactly where the data is coming from and where it's going to, what's failing, what's succeeding. It doesn't matter whether it's analytics feeding into a dashboard or whether it's a machine learning feature that's feeding into your fraud application. You see exactly how things are shared. That's the vision that I and many others have in mind that we're all working towards, where you just have this fully integrated view of all your different data producers, consumers, transformers. And we're, of course, far from that, where even today within the same team, you oftentimes don't have this visibility, let alone across teams in the same organization. And maybe at some point down the road, we can even have this type of visibility across organizations and not just within the same organization.
And for people who are considering whether and how to apply ML to their problems, what are the cases where a real-time approach is the wrong choice?
Real-time ML is not the right choice if you don't care about the information that happened in the seconds or minutes or hours leading up to the prediction. Like if it's one of those use cases where it's more about, hey, everything from Big Bang until yesterday, and that'll always stay this way. You don't think that you'll get much more juice out of the prediction by bringing in more recent real-time information. If that's the case, coupled with you making these predictions and acting on them in batch, like once a day or once a week, then that is a batch machine learning use case. And there's no real need to force real-time machine learning complexity on top of that. If, on the other hand, you need information up until the moment where you're making a prediction, or if you are acting immediately on the prediction as you make it and it affects the end user, then real-time machine learning is a good choice.
Are there any other aspects of the kind of real-time ML ecosystem and applications and the ways that you're working to help support those capabilities that we didn't discuss yet that you would like to cover before we close out the show?
I think we went pretty broad and comprehensive here.
Well, for anybody who wants to get in touch with you and follow along with the work that you and your team at Tecton are doing and the kind of future direction of real-time ML applications, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest barrier to adoption for machine learning today.
The biggest barrier for adopting real-time machine learning is typically that companies don't yet have the right tooling and the right platforms in place to actually make it easy to develop these real-time machine learning models and features that can be consumed by ML models that are running in production. That's, of course, why self-servingly we're going after this market, and we're trying to make it significantly easier for enterprises to have a system that is easy for them to develop real-time machine learning applications with.
All right. Well, thank you very much for taking the time today to join me and share your experiences of working in the space of real-time machine learning and some of the ways that it can be applied and how teams should be thinking about its potential for their problem domains. Appreciate all of the time and energy that you and your team are putting into making this a more tractable and approachable problem. So thank you again for that, and I hope you enjoy the rest of your day.
Thank you. Thanks for having me.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcasts.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachinelearningpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachinelearningpodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.